conference we organized in the past. And it's really nice to see the science reaches all the ages across. And I hope I can contribute a little bit to this. I think it's a great project that you have ongoing there. It's a bit sad that we have to do this in this in a really weird way, where basically I'm talking to a screen, and in a way I feel a little bit lonely here. But please interrupt me if you want to, and I would be very happy. I will try to go through a few slides as quickly as possible, so that we can have a lot of time for discussion. So today I decided to talk to you about how we transfer things in a human body. And that, of course, has a lot of relevancies on understanding human body biology, but also in how to design better medicine that can be more precise and more efficient in such a way. So, of course, the theme of the conference is the timeline, and I needed to start with one, particularly with the medicine one. And medicine is a science and now becoming a technology that has been with us since the arbors of human races, since we move on from a simple animal to a more collective being. And there, as a consequence of our first instinct to survival, we start to try to learn about our body and how we can cure it and repair it in a way that might actually prolong our life or defeat diseases. And as you can see, this is an effort that goes back to really the beginning of civilization. Probably the most famous doctor, Hippocrates, in ancient Greeks, and of course the ancient Chinese medicine. But for many millenniums and for many years, medicine hasn't really evolved massively. And then in the beginning of the humanism, after the Middle Ages, there was a bit of a revolution in understanding our physiology. And finally, in the last 150 years, medicine has advanced tremendously, and in a way that now we are really close to creating almost cure for every type of diseases. So one thing which has enabled such fast advancement is really our understanding of the human body, really putting the human body in a context of physical problems, understanding the numbers behind, trying to find out the physics of things within, and then from that really creating some sort of way to really enter it and manipulating and cure it if it comes to that. In numbers, the human body is very much a collection of cells. Actually, there is about 40 trillion of cells that comprise, in average, any human body. We take about 23,000 breaths per day, and that accounts for 115,000 heartbeats per day, and then typically a minimum of 1,000 to 1,500 calories, although I can tell you that you probably normally exceed that entry, and that allows to pump about 8,000 liters in one day through 42 billion blood vessels. So these 40 trillion cells need to communicate within each other. So transport within our body is critical. And that is very much fundamental for our survival, but because, of course, this is how you receive nutrients. And, of course, not only that is important to understand whenever, for example, when a disease appears, sometimes it's to do with transport deficiencies, but also to understand how we can use this transport to deliver stuff into our body. And thus, the most important part that control the transport are the blood vessels, the very easy one to understand. Blood vessels are distributed across the body. I already say the numbers are quite in the billions. But each part of our body is always supplied with a blood vessel. But at the same time, each part of the body is also supplied with another system called the lymphatic system. In this nice micrograph, which is a section of a part of a tissue, which shows in red the blood vessel and in green lymphatic vessel, it shows that basically everything that gets into the tissue also gets out through the lymphatic drainage, it's called. And so it's important to maintain such a balance. So materials get in and get out continuously for every tissue. And so the two systems work very nicely in synergies. And that makes sure that everything is actually transported into the right place. Then each cell is very much a container that contains a lot of proteins. As soon as you go down to the molecular levels, you actually start to observe that the things are no longer static. They actually fluctuate all the time. We're surrounded by water molecules, so a protein within our cells look exactly like this video created from a group in Harvard University a few years ago. And it shows that everything is quite crowded and packed in a very small place, and yet they work fantastically well in synergy, creating some very remarkable art, such as molecular motors, division, cell division, transport mechanisms, etc. There's a lot of things going on. Now, this video, though beautiful, is very difficult to understand. Let me give you a much simpler version. And this is a simulation that I created in my computer, where I show the most famous and common proteins encountered in our blood. The gray one is albumin. You probably recognize this Y-shaped protein as the antibodies. You have other type of antibody like the IgM, which has been very much in the news. And then you have lipoproteins, fibrogen, etc. Now, if we take a droplet of your blood, of course, 50% of it is made of cells, and you know the most common one being the red blood cells. But the rest, the water that bathe the cells, known as plasma, is never really just water. It's always a very enriched protein solution, where you really have so many protein effectively. If I actually pack in the right volume fraction, you have a very little space left for the rest. So the water here in the white colors is very nicely packed in within those proteins. So remember that everything in a biological world is extremely crowded and extremely packed. So we now trying to understand such nature. And for example, in my research group, we are very much interested in developing new microscopy techniques. Very recently, we've been working on a new concept called liquid phase transmission electron microscope. This is one of the most powerful microscopes that have ever been invented. Literally, electron microscopes allow you to look at single atom, and basically, you start to image things with a resolution of few nanometers. Remember, 1 nanometer is about 10, 20 molecules of water all lined up together. And what I'm showing here is a video of a protein called ferritin, which is about 8 nanometers across, floating and swimming in water. So that simulation I showed you before is actually very much what happens. This concept is called Brownian motion. It's very much typical in any liquid state environment. And our body is, for the large majority, made out of liquid. So this dynamic nature is critical to understand. So in my group, we try to then put this information, and we combine very closely physics and biology to study how transport happens in the body. And of course, there's some nice maths out there that we often abuse and use. We try to understand how things diffuse out of the blood vessels and then where they go and how they come back into lymphatic drainage, etc. We try to understand how things interact in such a crowded environment I show you. And we try to understand how those things can enter the single component of the tissue, the cell itself. And of course, the very first immediate understanding of biological transport is very much like an irrigation system. You have, let me run this video again. You have, this is an in vivo imaging of a blood vessels. You have basically the blood being pumped all the time, that then all the ingredients get through these barriers, the endothelial cells here, and they get diffused into the tissue. And then, of course, there is something which I don't show here, the lymphatic drainage that drain it out. So it's very much like a typical pipeline that you have in there. And as such, we can study this understanding fluid dynamics, how things move into the flow, how things diffuse without the flow, etc. And there are some really nice maths already available for us. However, on top of this traditional transport process, cells and biological systems have some very clever way to move around. They are very good at transforming stimulus from any stimulus from the environment, that being light, that being a spatial gradient into a surface, a chemical present into the environment, or even temperature, and transform that stimulus into a mechanical movement. The most famous of all is called chemotaxis. The video I'm showing here is the video of an immune cell called the neutrophil This is a very common immune cells in our blood. And this is literally a droplet of a human blood where you have the human neutrophils now that has been activated because it recognizes an aggressor, an invaders in the form of a little bacteria called Staph aureus. And as you can see, the neutrophil sense that the presence of the little things, and it starts to move, chasing the little things around, avoiding the surrounding red blood cells, making sure it doesn't touch them because he recognizes them as their own. And then it only stops when it has finally eaten up the little bacterium. And that process called chemotaxis is really important. This is very much one of the most important stepping stone in evolution. You know, going at the very beginning of a life, a biological life, a single cell has developed this ability of moving, of locomotion, and that created a huge acceleration in the complexity and evolution, etc. Chemotaxis is present everywhere in our body. It really regulates not just immune response, like in this case, but also how tissue grow and develop, etc. And it's a very clever method to really move from A to B, very effective. So once we know all of this, how can we convert such information into new medicine? How can we make our medicine using the same principle of biological transport in order to become more efficient? I don't need to say to you that whenever you open a new medicine in a pill box, you always find that really long prospect that tells you for what the medicine is good for, but also tells you that some medicine can come with some really nasty side effects. And the reason you have side effects is because those medicines, although designed to do good stuff, often they interact with other parts of our bodies where they don't do what they're supposed to do, or what they're supposed to do is not in the right place. And so that creates a lot of side effects. And indeed, creating a system that takes our medicine more or less into a very sort of precise way towards its location where the medicine is needed is very much our dream of scientists. So my group, the other half of my group, basically take information from the physics and biology, which I just introduced to you, and then convert those into building principles, into new challenges to tackle in order to get our medicine to the right side. Effectively build a navigator. Of course, these navigators are going to be very, very tiny because they have to go into human body. And so our tools of building are not the traditional engineering skills that you probably see in mechanics, in construction, etc. We had to deal with much smaller building blocks. We literally go down to the atomic level to really build and put those atoms together into the right form and shape. This is known as nanotechnology, and this nanotechnology now has promised the revolution in many different fields, from energy to materials. I quite like this video that IBM published a few years ago. This video actually took months of work, and effectively, where you see every little pixel is a single atom of copper that is being manipulated using physical tool called scanning probe microscopes, and then putting together into a very precise way, well, more or less precise, creating this really cute cartoon. Now, this is, of course, an extreme way of manipulating matter, but effectively is a great example how close we are in really transforming matter molecules into building blocks and materials that we can put together, and engineering things a little bit more complex, of course, than a cartoon. Perhaps maybe a little carrier, so a little navigator, like I told you that. So in my lab, we use a concept called molecular engineering, where we really make molecules from scratch. We use synthetic chemistry to construct single molecules. We put together these into bigger molecules, macromolecules called polymers, and then we use those polymers to create even more complex structure, building them into the functionality we require for the single purposes. And of course, in this case, you know, if our challenge is making a pill, the very first structure that we like a lot is what is called a capsule. Now we use a technology where creating a bottom up from water is called, the capsule is called vesicle. So you will see this name more and more times in my slide. Now, What is next? So what are the challenges? Of course, there are many challenges, but I really decided to focus on three critical ones. Of course, locomotion. I already showed you that is critical. Guidance. How do we decide where our pills goes is fundamentally making sure our system goes into the right place. And then effectively delivery. Because you can design the most nice, the nicest of the carriers. And indeed, if this is not capable, then not deliver the cargo, that the job is completely unfinished. Of course, sometimes and often, depending how we present these things, we can call them as a robot. So effectively, they have a series of function and complexity that get closer to the robotics level. And of course, because this is a nanoscopic system, we sometimes often the nanorobotics comes to mind. And in other occasions, I presented those as a nanorobotics feat. But this is a name that you can use or not, depending how you want it. But effectively, what we're looking at is a carrier anyway. Now, how do we get locomotion? And to show you that, I'd rather go for a very specific example in the human body. And actually, this is something that has been occupying my research activity for over 10 years. And although we really like to work across the field of medicine in the last 10, 20 years, 12 years, we focus a lot of our effort into the brain. The brain, of course, is not, I don't need to explain to you, it's one of the most important organs in our body. And it's very, very unique to the human biology because we have one of the biggest brain compared to our body than any other animals in the biological world. Our brain is extremely expensive from an energy point of view. Even though it's only 2% our weight, it consumes up to 25 to, in some cases, even 60% of energy. And that is possible because remember the vasculature I was telling you about it, that really feeds our organs with energy and nutrients. The vasculature that feeds the brain is special. It's called the blood-brain barrier. And the reason it's called barriers is because it makes the brain composition very unique. It's very different from any part of the body. The things that can get across and can get in and out of the brain are very specific. And the brain is very fast about it. It only allows a few molecules to go through. Now, that means that if you want to make a drug that gets into the brain, effectively becomes almost impossible to reach, unless you create damage, of course. And so, as from the pharmacology, we learned that 99% of the known drugs cannot enter the brain. And that is quite a difficulty when it comes to, of course, curing diseases like Alzheimer, Parkinson, dementia, schizophrenia, epilepsy, brain tumors, and anything to do with the brain going wrong in that sense. So this is a big challenge in general in medicine. So what do we do there? If we figure, let's step 20 years, 30 years ahead in the futures. So what we need is a system that goes into the bloodstream and navigates the bloodstream, potentially creating a system that, of course, has to be very, very stable. Remember, all of these factors are not simple and they require years of work, but the system needs to stay in the blood. They need to operate in that crowded environment, which is our bloodstream. And then needs to be pumped inside our circulatory systems, potentially avoiding interaction in any part of the body but the brain. And once it reaches the brains, really need to get across that vasculature, which I already told you is very difficult to get across of. And then once it does that, he needs to really navigate his way through the brain. Now, the way, and I'll show you how that happens, that these things that get across the blood-brain barriers are not simple and require a lot of knowledge of biology. So how do we feed our locomotion? Let's go one challenge at a time. How do we make sure that our system only sticks to the vasculature in the brain and not any other part of our body? So recently, we found a way that we can copy that chemotaxis ability of cells to move. This is not data from my lab, but this is the data that I taken from a group in the US, in Canada actually. And then these guys have been able to make in microparticles, small particles. Each of those dots is about 10 microns. Think about it, that one of your single hair is about 100 microns, just to give you a measurement contest. But these guys have been pretty good at making these little particles. They can move them really nicely. And what you see right now in the movie on the left corner, that a particle actually handling single cells and moving it around. So this concept of swimming and locomotion is becoming very popular. And now we have again, going back to the name Nano Robotics, really we can use this concept for really moving stuff in a controlled fashion. And effectively what you need is really engineering your system in a way that transform and react to something in the environment, typically called fuel molecules, and then transform that fuel into a manipulation of the water around the object. And that, of course, the manipulation is to be in a way that the water is really moved so that our object can swim and really go towards that chemicals that we target. Now, in the case of the brain, the chemicals we want to target is glucose. I already told you that the brain consumes quite a lot of energy, in particular for the glucose. Our brain consumes about 60% of any glucose intake that you have every day. So when you take glucose, or the glucose is transformed from your food, 60% of it goes into your brain. And that is possible because the capillary, the vasculature of our brain is extremely permeable to the glucose. It's got a lot of molecule called GLUT1, which effectively grab the glucose and pump it across. And the brain vasculature has many of these GLUT1. So that basically once you reach the brain, the concentration of glucose is much higher at the wall than in the core, where what is the case in our system. So we have a source, a fuel, a locomotion. Next, how do we guide our system through? That is very much the essence of medicine. This concept of specificity, of targeting, goes back to the beginning of the 20th century, in particular with one name, Paul Ehrlich. He was a Nobel laureate in 1908, one of the very first one in medicine. And he already, even 3 years after Einstein, Annus Mirabilis, and this Annus Mirabilis is the year where Einstein discovered and introduced the concept of, amongst many things, of molecules. So back in those days, people didn't really believe in molecules and atoms. So that was how innovative Paul Ehrlich was. And yet, he came up with this idea that molecules can interact specifically with biological objects, and he came up with these ideas of ligand receptor, side chain theories. Back in those days, everything was called the magic Kugel, or the magic bullet. So basically something that really can create specificity, that chemical sense specificity. Now, going in a more complex form nowadays, this specificity, unfortunately, is not just something that involves one molecule, but actually cells have a collection of molecules. They don't just have one type of receptor, they have hundreds and thousands of type of receptors. And so what we do in our lab, we create this combinatorial game where we design our system such as interact exclusively with that compositional receptor. So what we call phenotypic. The phenotype of a cell is basically what define the cells in terms of compositional properties. And so this is one thing that we really been studying and trying to understand. So finally, how do we get into the brain? Of course, we understand how different is the brain vasculature from the rest. So we transform that information to targeting moiety, and then eventually we actually can get across. Now, finally, the last bit is delivery. So once we reach the cell surface we want to target, now how do we make sure our system, our little carriers, is then efficiently delivering their own cargo? And now one thing you guys need to learn about cell biology, the cells take up materials using a process called endocytosis, where really literally they ingest the particles, the cargo, wrapping up in the same membrane that created the barriers, and they take it into little compartment called endosome, where everything is acidified. There is an acidic environment. It's very much like the stomachs, our stomachs, where you digest whatever you're taking up. Now, this digestion system involves acidification, so we can use this concept to trigger a disassembling process. Remember, our systems are created by molecular principles, so we can introduce a molecular principle that responds to the acidic environment of the interior of the cells, and so therefore our system, as sophisticated as it disassembles, it falls apart. And so that means that whatever we have encapsulated into our little carriers now release into the cell. And that, of course, makes our system very efficient in doing that. Right, so let me finish up with a little animation to wrap up all of these concepts into one single system. So this was a paper we published in 2017, where we showed that we can create this little capsule called vesicles, about 100 nanometers in size. We can load them up with a lot of different things. And then being so small means these things normally are completely without control. They just, once we put them in water, they're subjected to this Brownian motion. The water molecule hit them differently from side to side, and they're literally buffeted all the time around. So they have no way of controlling their movement. But if you understand the dynamics of this, if you understand how to manipulate these collisions around the particle, in other words, making sure that our particle interact with the water in a very different way to avoid this sort of randomness, then the things changes. And indeed, we do that by creating an asymmetry into our system. It's something that where on that side, the water and a given molecule interact very differently from the others. And so effectively, you create different behaviors or molecular reactions across the structure, and that in terms transform into really making our system moving and swimming in the same way as I showed. Now, if you then make this responsive to glucose, you know, when those particles going into the blood, they will stay mostly in the center. But then once they reach the brain, where the glucose is very much pumped into it, then that creates a chemical gradient that we can follow. And now, remember, if you make those particles interacting with the blood-brain barriers, then those things can go inside, and we can deliver the goods as we've done with that acidification process. And with that, I stop showing you some of the experimental data that we collect in our data. This is the brain vasculature of a mouse. The green bits that you see is our little carriers, which is made across the blood-brain barriers. And the horrible graph on the left shows you that the carriers can deliver some sort of goods. In particular, in the last years, we showed that we can use it, for example, to help after stroke. You know, stroke is this horrible disease that is actually one of the worst killers in the world, where basically the vasculature of the brain is broken and creates a lot of inflammation and damage locally into the brain that can cause a neurological impairment, etc. So what we show is that we can deliver drugs into all brains that protect the brain from this damage, limiting the damage caused by the stroke. And now, actually, because we use this such effective way to deliver stuff, we can deliver 1,000 times less drug required, and so therefore avoiding side effects, etc. And with that, I stop here, and I guess I just stop sharing. And I don't know whether you want me to switch on my camera so you can see my face, but that's not necessary. And then I can take questions if you want. Thank you very much for your attention.
Thank you so much, Professor Battaglia. It was so interesting to hear how your research is uniting these sciences to find new innovative approaches to all of these issues in the biomedical sciences. And I found it really interesting to manipulate how cells move to solve issues in brain disorders such as Parkinson's and dementia. So if anyone has any questions, please send them over to YSJ Celestine in a private chat, and we'll be happy to answer them. So our first question is, how could some of these methods you talked about be applied to COVID-19?
Well, this is a very good question, actually. And you know, many scientists activate the energy towards COVID when it started, and when we discovered what the disease was at the beginning of the year, and we did too. So one things there are two things that are very important from our research towards the COVID disease. First of all, the virus itself is not very dissimilar from what the type of materials that we produce. And so the viruses also plays the same trick that we try to play in order to get across the barriers. So for example, we are applying our physics and mathematics knowledge on nanoparticles and multivalent interaction to really understand how the virus spreads in our body, and we discover something which is not trivial. So for example, to give you an anticipation, we discovered the virus doesn't need to have a lot of receptors to bind, and after when you have too many receptors, the virus doesn't bind. So it's kind of an opposite what normal people expect. On the other side, we can copy the virus using our nanomaterials, and then making sure our medicine goes where the virus is, so where the virus is causing damage. And so what we have now started big programs on that, where we're creating our nanotechnological tools to really make sure that the antivirals, the anti-inflammatory drug that really are useful for stopping a disease, are delivered exactly where the virus is creating most damage, and so that we can create a much more efficient therapeutic response.
Thank you. We've got another question now. What do you think are the greatest challenges in this field?
So one of the greatest challenges which I encounter sometimes is just simple communication. Unfortunately, science has become so vast and so big that inevitably we all specialize in our own field, creating our own languages, and often we forget that we can actually work together with other scientists in order to tackle a common problem. So in my case, I need to work with physicists, I need to work with medics, I need to work with biologists and chemists. And sometimes the communication can be a problem across the disciplines. And this is one of the biggest in terms of social interaction. Then in terms of general challenges right now in our human body, even though we know a lot of information, the biology is not yet disclosed. There is a lot of things we don't know. For example, in the brain, while we know more or less how stuff gets in, we have a very little understanding how stuff gets out. And so there is a lot of knowledge there to be acquired yet, and that is critical when it comes to medicine development. In medicine, the concept of selectivity is still a big challenge. We think we have a solution for it, but we're not really sure it's going to be that solution. But clearly, one of the problems we have with drugs often is that the drug is, although potent, goes in part of the body where it creates damage rather than the therapeutic effect that it should. And so that is a challenge. Selectivity is a challenge. But I think there are, of course, other challenges as well, but I think these are probably the most important ones.
And what advice would you give to an aspiring scientist?
Feed your curiosity. One of the major skills for every scientist is to be curious. Really answer as many questions as possible, but also bear in mind the more questions you answer, the more questions you're gonna end up with, right? And this is one of the curse on knowledge. The more you know, the less you know, and that is very important. But that's okay. Don't be discouraged about that. Actually, it's really important you reach that kind of level of realization when it comes to understanding and knowledge. And curiosity really is very much our driving force. Learn your fundamental sciences. Don't be afraid to go. If you are a biologist, don't be afraid to do math. If you're a mathematician, don't be afraid to do biology. I think it's really interesting how scientists can give you tools in our own discipline, even though that is very far away from what you normally do or what you normally like. Actually, sometimes they give you solution in a way that you don't expect. So be really open to all the different sciences. Right? The curiosity is really the very first. Don't stop it. Always feed it. Yeah.
And someone's asked, what are the scopes and limits for the organs that can be targeted?
Of course, that really depends on the medicine. So typically, the way we operate is talking to clinicians first. So they tell us what are the challenges, what are the diseases. So in the first part of the challenge, you need to know how the disease works. You need to know which part of the body is affected, which cells are behaving badly, which cells are damaged, and then at the cellular level, which protein you need to target in order for your drug to do and to stop that damage or to correct that deficiency. So that biological and biomedical information is fundamental for us, and we need that first of all. And then once you have that, then transforming that into a cure, it's not easy task because like I say, you need selectivity. You need to make sure your things go exactly where it's supposed to go. In some cases, like in the brain, you need to really that selectivity needs to combine with this ability of getting through those barriers that surround the organs and making the organ more inaccessible. And all of these avoiding interaction which are unwanted, and all of this controlling interaction, that game of energy is critical. So, but effectively, once you have a disease and information on the tissues and the local biology, the way of translating that into medicine or medicine development is not impossible. It might take time, probably in some cases years, in some cases tens of years, but it's possible in most medical fields.
And has this new form of nanotechnology been applied to treat diseases, or is it still in development?
So the problem with clinical development is a very tricky business for two reasons. First of all, before you actually get into the clinic, before you actually get injected into humans, you need to really demonstrate that your technology, your new medicine is extremely powerful. So it's not like you're developing a car which is 10% faster or more safer than the previous one. That 10% in medicine needs to be 100%. The only way you justify a new medicine is by having really a game-changing difference. So you really need to improve every time massively your approach. And then the other aspect is, of course, safety. It's not that I can design anything in my lab and then tomorrow they can go into the hospital and be injected into patients. That transition from the bench to the patient, it can take as long as 20 years sometimes. There is a lot of clinical testing that you need to go through. You need to really ensure safety, clinical safety, toxicity. You need to really predict any side effect, and all of this takes a lot of time. So as such, these concepts which I presented, some of them actually we are pushing them into the clinics, and we have one particular formulation where we are tackling brain tumors, where hopefully, if we manage to work it out in the next 4 or 5 years, we might actually get a first clinical trial going in 2 or 3 years' time. But that is really predicting, is not entirely set in stone. Then the other similar things where your pills is smaller, so nano medicine or medicine where you have a formulation which are really tiny, they already been used in the clinic. They're not as sophisticated as what I presented today, but there are a few examples already for oncology and infection where you actually, some of the vaccines that have been developed right now for COVID, for example, are in a way, at least in terms of formulation and construction, are very similar to the approaches I presented here. But I think before we can actually see a nano robot in a human body will take at least another decade of clinical trial.
Okay, thank you so much for such a fascinating talk and the responses to all of those questions. And also a big thank you to everyone who's here watching, and we hope you've enjoyed it as much as we have. Just a quick reminder that we'll be having some really exciting student presentations starting at past, and the links to access these will be in the chat. So thank you so much.
Thank you very much for having me, and I hope you enjoy the rest of the conference. Thank you. Bye.
Great, thank you so much, everyone. I'll shortly put down the link to the student presentations on the chat. To see who exactly are presenting in each of these sessions, as we have 2 parallel sessions, you can see the program that Sona has sent to you previously. Once again, thank you so much for coming. Thank you so much to Professor Giuseppe Battaglia for speaking with us. We've gladly enjoyed this talk.